So this is electron transport chain, or ETC, sometimes we abbreviate it, and how it's linked to oxidative phosphorylation, or OXPHOS, is what a lot of places will call it. Okay, and so these two are irrevocably linked. You can actually uncouple them, which that does have ramifications. There are times that you want to do that, and there are times that you don't. Okay. Yeah. So technically speaking, the ETC has 4 multi-subunit membrane-bound complexes, okay, which they are numbered, complex 1, 2, 3, and 4 in Roman numerals, but they also have official names. And their official names tell you exactly what they do. There's no mistaking it. And it has 2 electron carriers, coenzyme Q, okay, which is ubiquinone based, and cytochrome C. This is where all those FADH2s and NADHs that we've been making and all the other metabolic pathways get cashed in. It's sort of like if you went to like Chuck E. Cheese or the Showbiz Pizza and you got all those little tokens, and now you get to cash it in for some cheap little, tchotchke. Except ATP's in a little cheap tchotchke. Okay. And the electrons are transferred one at a time. Ultimately, and this is where some people get confused, it's not the ATP that gets the electrons. The electrons have nothing to do with ATP. The electrons ultimately go to reduce oxygen to water. And so how does that work? Like how does the ATP actually get made? As part of the oxidative phosphorylation, it's not the electron transport chain. How does the ATP get made?
Hydrogen is going through ATP synthase.
Right, and it really does look like a little turnstile. I mean, it's like it's a little gear. It's really cool. But it reminds me of a turnstile, like at the subway or to an amusement park or something. And so the protons go through, and it turns the turnstile, and it forces the ATP to be made. We'll see that later on in a video. Okay. So I think this is actually from an older book, but I like this little cartoon. One thing that I like about it, I don't know how easily it shows up here, is that there are 2 pathways. You never, ever, ever, the electrons never go from complex 1 to 2 to 3 to 4. That would be too easy. You have 2 possibilities depending on whether you're starting with NADH or FADH2. If you start with NADH, just ignore this one, because that's not actually part of the electron transport chain. If you start with NADH, the electrons get transferred from complex 1 to 3 to 4. If you start off with FADH2, you bypass complex 1 altogether because it goes from complex 2 to 3 to 4. So that's why, depending upon where the electrons are originating from, is where you start. Okay, if it's NADH, you go through 1, 3, and 4, and if it's FADH2, you go through 2, 3, and 4.
1, 3, and 4, but you don't go through 2.
Mm-mm.
Those Qs are electrons?
No, Q is coenzyme Q. That's just a little cartoon. And cytochrome C, which they don't, it's kind of hard to see, but it's this little one that's actually not in the membrane. It's the only part that's in the intramembrane space. It's a relatively small protein compared to the others. All right, so we have the matrix. Make sure you know where all the parts, everything's occurring. We have the Krebs cycle. It's occurring in the mitochondrial matrix. Where is glycolysis once again? Cytosol. Where is urea cycle? Cytosol and the mitochondrial matrix. That official step 1 and step 0 is in the matrix. And then, of course, gluconeogenesis is similar, where it I just did the wrong one. It's going to change. Let's see. There we go. Where gluconeogenesis goes between cytosol and mitochondrial matrix and back out to the cytosol. So we have the NADHs and FADH2 here inside the mitochondrial matrix, and the protons are being pumped from the matrix to the intermembrane space, but sometimes I abbreviate that as IMS, just in case I write that someplace. That's what I mean. So is the pH of the intermembrane space going to be high, or is it going to be low? It's low pH because it has a high concentration of, or higher concentration of the protons. And it's going to be the opposite in the mitochondrial matrix, but it's going to be a higher pH with a lower concentration of protons. And that's really important because then you get all of these protons out here. They're wanting to get back into the matrix. And so what they do is they cross through the little turnstile and they force the ATP synthase to make ATP. Okay. All right. And that's just what this is showing. And this is just another cartoon depicting the same thing. It's just in case the other one you found confusing. This one has the proteins removed just to show where the proton movement. All right. And so this proton gradient establishes a voltage gradient. So there's an electric potential because you have all these protons being pumped out into the IMS. And so it's this difference in the concentrations that's going to force ATP to be made. And there are a few books that call it ATP synthetase, but technically it's not a synthetase, it's a synthase. But it's ADP plus an inorganic phosphate, which we can get that from either just the hydrolysis of other types of ATP or the hydrolysis of inorganic pyrophosphate. And it makes ATP in water. Technically, the water can also come from the oxygen from before. Okay. I do not know, I haven't checked to see if the song works yet, so I'm not going to click on it at this point in time. But there are lots of videos and songs and things out there. And also, this one seemed to be a very popular one that my students have done in the past for making videos. In fact, one of the ones that's been watched the most, in fact, it used to be watched the most of all the student videos, was on the electron transport chain. And it's funny because they had like a little behind the scenes making of portion of their video. Okay, so we're just going to get started here. Complex 1 is also called NADH, Ubiquinone Oxidoreductase. So you can probably guess what this does. What kind of reaction is this going to be doing if it's called an oxidoreductase? It's transferring electrons, right? It's a redox reaction. And in particular, is it going to be oxidizing or reducing the NADH? It's oxidizing because NADH is losing its electrons. Ultimately, ubiquinone is going to be reduced to you're going to find out it's going to be reduced to ubiquinol. Okay. Now it's not direct. None of these are direct. They're very complex. These are huge protein complexes. This one requires FMN, which is the F part of FADH2. It's a flavin. And it has an iron sulfur protein in it. And then ultimately coenzyme Q. And I will give you a heads up that that I do really like a lot of the, in case you haven't noticed, I like a lot of the health-related and the suggested problems at the end. At the end of each chapter, I can guarantee you that at least some of those will be on the exam. Then we have complex 2, which is succinate dehydrogenase. It's also called succinate coenzyme Q reductase. Where have we seen this one before? This is the citric acid cycle. This was the one, remember all of the citric acid cycles in the mitochondrial matrix except for one enzyme which is attached to the inner membrane of the mitochondria. This is that enzyme. And it directly links citric acid cycle to the electron transport chain. Because if you remember, it makes an FADH2. The FADH2 can then just go directly into via this complex to the electron transport chain. And it also has some special parts to it. It's got one of my favorite hemes in there, which I don't know the rhyme or reason on how they named the hemes, so I have to apologize now because they give them letters and they don't all make sense necessarily. I don't know why they came up at the same time, but then we have complex 3, which is the one that I worked on, which is called cytochrome BC1 reductase. So what do you suppose it's going to be doing based off of its name? If it's called cytochrome BC1 reductase,
Reducing cytochrome.
it's reducing cytochrome BC1, right? And ultimately, it gives its electrons to cytochrome C, and cytochrome C jumps from complex 3 to complex 4, and then complex 4 is called cytochrome C oxidase. So what do you suppose it's doing? It's oxidizing cytochrome C. Okay. This is where I'm going to end for today, and then we'll pick up, on Friday, right from here.